Well, good morning, ladies and gentlemen. Welcome to 1.01, the scientific method. This video is aligned with the Physical Setting Chemistry New York State Core Standards. My name is Mark Rosengarten, and I will be taking you through the course of chemistry, and I hope you enjoy it, and I hope you get a lot out of it. So, here is the situation. People think that science is nothing more than just a collection of facts, that it's books filled with knowledge, and nothing could be further from the truth. Science is a process. It's not a body of knowledge. It's how we achieve that body of knowledge. And today we're going to take a quick overview as to how exactly this scientific method works. The scientific method, like we said, is a process. We start with a question, something we observe in the real world. It can be as simple as, why didn't my car start? Or it can be as complex as questions about the very nature of the cosmos itself. Whenever you make one of these observations that leads to a question, and we want to answer that question, what we need to do is first do some research. Find out what people have tried to figure out before us. And then we're going to use that research to create a list of possible causes for the observation that we made. When you go to a doctor, the doctor doesn't just automatically know why you're sick. What the doctor does is take a look at the evidence before them and try to figure out what is it that could be causing this problem. Do some research. What are some of the things that could cause you to be feeling the way you feel? And then arrange them in order from most likely to least likely. And then test each of those one at a time. And this is true of every kind of problem solving. This is not necessarily for science only. So, to create a hypothesis, this is not an educated guess. This is a fairly common misconception. A hypothesis, all it is a prediction that you make based on the research that you did. And you say, if I do this, which we're going to call the independent variable, and when it gets graphed eventually, when we get to the analysis part of things, we're going to plot it on the x-axis of our graph. If I do this thing, then this result should occur. Cause and effect. We're going to call the effect the dependent variable, and we will graph it on the y-axis when we do our analysis. So if I do this, then this should happen. So for example, let's say I want to test the effect of changing temperature on the rate of a chemical reaction. If I increase the temperature, then the reaction rate should increase, because the hotter the system is, the more frequently the molecules will collide with each other, and therefore more reactions will occur in a shorter period of time. And that you would get through researching, which you'll get in a unit later in the year called kinetics and equilibrium. And then you conduct an experiment. Now, the experiment is the phase where you actually test your hypothesis to see if it's true. If you say, if I increase the temperature, well, then increase the temperature. Then the reaction rate should increase. Well, actually measure the reaction rate to see if that's what's happening. And when you do the experiment, you're going to collect data, which will be set up in a table form. So let's say you want to test the temperature, the reaction rate at 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, 50 degrees Celsius. Then on one column of your data table, you will pre-fill that in with the temperatures you want to test the reaction rate at. And then as you do the experiment and collect your reaction rate, you'll put that in a column dedicated to reaction rate. And therefore, you can have numbers right next to each other. And in many experiments, it's possible to collect a large number of measurements. So to make sense of these measurements, the next step is to analyze the data. In chemistry, this will frequently be done by graphing your data to demonstrate the relationships between the variables. Is it a direct relationship? Well, in that case, you have a linear equation, and you can actually create a y equals mx plus b formula to relate your x axis to your y axis. If it's an inverse relationship, you can develop a function for that. And if it's some other function, if your data follows some other mathematical function, then that mathematical function can be used as a formula to make future predictions in case you need to test it again. Then you reach a conclusion. Did you have a supported hypothesis? When the temperature increased, did the reaction rate increase? Well, then your problem is solved. If not, then your hypothesis, your prediction was incorrect. And you're going to need to start the process all over again. It's a systematic way of eliminating possible answers to a problem, one at a time. Now, when you do your experiment, you need to make sure that you hold every variable that could have an impact on the outcome constant. If I'm going to test temperature versus reaction rate, I need to hold constant every other possible thing that could impact reaction rate: concentration, pressure, surface area. Anything that could affect reaction rate other than temperature, we will hold constant throughout the experiment. So just to recap, you observe the phenomenon. Why does it happen? You construct a hypothesis, do some research, and make a testable prediction. And by the way, if you want to see some really good testable predictions out there, you might want to check out these guys. Yeah, they're no longer making new episodes, but the Mythbusters is a really good way to show how hypotheses can be created and tested in a very entertaining fashion. Avoid this. When you ask the question, why is my car not starting? Well, you might want to pull out your phone and do some research and then track it down one thing at a time. You don't want to check the engine, the gas in your car, and to see if your battery is dead all at the same time. Test your battery first. If that doesn't work, check your gas. If that doesn't work, then you can start checking off things in your engine one thing at a time: your spark plugs, your starter, and so on. So a hypothesis is not an educated guess. It's not a guess at all. It's a prediction. This would not be a hypothesis. This would be the epitome of a guess. Actually doing the hard work is what's needed to make the scientific method operate in your favor. You design and carry out the experiment. By the way, this is just a cute graphic. It looks like all that's going on here is some dry ice in a container of water that's had some blue food coloring added to it. Yeah, don't fall for this. This is actually just, a fun graphic. The experimental design must test only the variables that your prediction is based on. If you say I do X, then Y will happen, then you only test those two variables, and every other variable will be your control. So if you say I do X, you do X. Since you control that, that's the independent variable. Y should happen? That's the effect of your cause. That's the dependent variable. And you'll graph it on the y-axis when you do your analysis. The independent variable will cause a change in the dependent variable. Then you're going to collect your data. You're going to record each step in a data table, and it is always recommended that you do more than one trial. because every time you do a trial, a little bit of error creeps into it. For example, if you're timing, you're probably using a stopwatch. And if you're using a stopwatch, you have to take into consideration that there's a little lag time between when the eye sees a thing and when the brain records that it's happening and then sends a signal to your finger to push the stop button on your stopwatch. So there is inherent observer bias and error that creeps into every observation. So always do multiple trials, because multiple trials will help eliminate this kind of bias and error. And then you analyze your data on a graph. Using this, we can see the relationship. As time increases, the number of cells increases, and it looks like it's doing so exponentially. So what we do is we take this particular curve, we find a function that fits it, and we create a math equation so that if I want to know, well, if 500 days goes by, how many cells can we expect? You just plug 500 days into your equation, and it will tell you how many cells you get out of it. And then you reach your conclusion. Did your hypothesis test out? If yes, yes, awesome. If not, well, then go back and start over again. Now, a word on the word theory. Theory is not an idea. If somebody tells you, hey, man, I've got a theory, no, they don't. They're lying to you. Either that or they don't understand the meaning of the word. The meaning of the word theory is very specific. Theory is a model that has been developed through a tremendous amount of experimentation, and not efforts to prove it right, but efforts to try to prove it wrong. You throw everything you can at this theory to see if it falls apart. And if it continuously fails to fall apart, then you know the model is useful for making predictions about things that happen in the future. This is different from natural law. Natural law is just basically an observation about things that always seem to happen. Like if I let go of a pen, it always falls, hence the law of gravitation. If I do a chemical reaction, the mass of my reactants is always equal to the mass of my products. Therefore, the law of conservation of mass. A law does not explain why this is taking place. It's just saying that it is taking place. A theory explains why, and it does so every single time flawlessly. Now, if you think you've got a better theory, not only does it have to take into consideration everything that has already been covered by this theory in the past, but it also must be able to withstand the same kind of scrutiny into the future. Theories can change with time. That doesn't mean that science is flawed. It just means that we are constantly improving our vision of what the universe is like and how it works. And that, ladies and gentlemen, is the scientific method. I thank you for joining me. And until next time, this has been Chemistry Review. View. I don't actually have an echo effect. I'm sorry. Bye.